fluctuations. We can calculate it in a large S expansion. I won't show you, that's complicated. But in a large S expansion, you find that this thing is actually order 1 over S and actually negative. This fact that it's negative is interesting and important. You might think this would be prohibited because this is kind of a 4th order term and this looks like a 2nd order term. But you can check that it's allowed for this to be negative and still have this action be bounded. A very simple exercise to show that actually this is always less than this one. And so this theory is stable provided this parameter is greater than -1. So knowing that, now we know the range of parameters, we can analyze a saddle point. So we just need to minimize this action. And it turns out that the solution to the saddle point equations have a form like this. Basically, they have a constant magnetization in the z direction, and in the xy plane they precess around. So this is what's called a cone state. If you were to look along a chain, the spins would be kind of sweeping out a cone. The saddle point solution will give the parameters of this cone. It'll give you the angle of the cone and the pitch of the cone as a function of the deviation from the critical point and the size of the field. And the most important feature that comes out of this is that actually, in some range of parameters, if we look at the magnetization versus field, it actually jumps. So at low field, you have this cone state, and above a certain field here, a critical field, the magnetization jumps all the way to the ferromagnetic state. So this is something called metamagnetism, where it looks a little bit like a ferromagnetic transition, but it happens at finite field. So in fact, this saddle point has 2 regimes. There's a regime basically when this parameter v is less than -1/4, where you see this metamagnetism. Whereas if it's bigger than -1/4, or if it's positive, there's actually a 2nd order transition between the ferromagnetic state and this cone state. So at this point, the cone, on the right-hand side, what happens is you have the ferromagnetic state, and as you go below the saturation field, the spins just slowly cant away. So this corresponds to Magon post-condensation. Over here, what happens is, before you reach the point at which there's a local instability of the ferromagnetic state, the spin actually just jump down to a non-zero canting angle. So we see that this is there are 2 generic behaviors, and one of them is this metamagnetism. And we expect, based on calculating this parameter v, we expect actually for the spin 1/2 case that we're in the region of metamagnetism. Okay. So what this analysis, saddle point analysis, is really controlled by the deviation from this critical point. So it's asymptotically exact when we're very, very close to this zero field critical point. So what it tells us is actually we have a kind of an exact solution for the behavior very close to this regime. We expect from the solution that this actually, in this region, we have a 1st order metamagnetic transition. So we learned the answer to one of the questions, which is actually that this cascade of multipolar phases is not infinite. It terminates in some metamagnetic transition over there. And everything about that metamagnetic transition we can calculate. For example, these are not sketches of the magnetization. This is the exact form of the magnetization curve. There. Okay. So now I want to try and move beyond this saddle point approximation. Okay, so this is kind of the leading exact approximation close to the critical point. But what happens when we go beyond it? So you should be a little bit concerned about the saddle point calculation, because I've told you that according to the saddle point, actually the solution is a cone state. And in one-dimensional system, it's not possible for a one-dimensional spin chain to be magnetically ordered. So what does it really mean that it's a cone state? It's still true that the saddle point approximation is controlled, but it's the leading approximation. We need to look at fluctuations beyond the saddle point to get the proper long-distance behavior. Yeah. It predicts the red line, and so any physical property you want.
So there's no, 5 or 6 different type of mechanism.
Okay, so the calculation doesn't actually, we'll get to this, so it doesn't actually tell us where this ends at this point. It says that arbitrarily close to this point we have this 1st order metamagnetism. So it tells us it does end.
Does end.
Yeah, so there is a maximum it tells us there is a maximum
So there
multipolar
should
order.
be another critical magnitude.
Yeah, so as drawn here, there's we know that there's an endpoint to this metamagnetism. That'll be one of the questions we try to understand. So what's the nature of that endpoint?
Okay.
Any more questions? Okay. Yeah, so these are kind of the three issues. So what is the nature really of these ordered saddle points when we include fluctuations beyond the saddle point? How do we describe the endpoint of this metamagnetic line, and how do the multipolar orders arise? Okay. So let's talk about the first one, the effects of fluctuation. So in zero field, the saddle point answer is a cone state with a canting angle of pi over 2. So the spins are just in a single plane. There's just a spiral state. So that spiral state, again, is not something that can actually order in one dimension. It can actually break the spin rotation symmetry. So we should really describe it by a nonlinear sigma model, which is very stiff. That's what it means that we have this good saddle point approximation. So what is that nonlinear sigma model? It's described in terms of the order parameter of the spiral phase. So the spiral phase actually is described by a SO3 matrix order parameter. So to describe the spiral, you need to specify the plane of the spiral and then the angle of the spins within the spiral. So that's described by two orthogonal unit vectors, E1 and E2. And together we can build a third one, E3, which is the cross product of these two. And together they just form the three columns of a 3x3 matrix, which is actually a SO3 rotation matrix. And so one can write down a nonlinear sigma model for this, which is a matrix nonlinear sigma model. It turns out that such a nonlinear sigma model has a topological term, which counts the number of times that this SO3 matrix winds the sphere. So it turns out that an SO3 order parameter in 1 + 1 dimensions has a Z2 topological number, which is called a Z2 vortex. There's a little demonstration. I don't know if you know this. You can think about your arm extending from your shoulder to your hand as a curve, okay? And there's a particular relation between your shoulder and the beginning of your arm, which is a coordinate frame. And now I can establish another coordinate frame, which is that of my hand, and I try and twist it around. I can twist it once, and I've gotten it back to itself, but obviously there's a non-trivial winding between my shoulder and my hand. I continue it around again. I do it twice, I get back. So this is a good trick for waiters. But this shows you that that pi 1 of SO3 is Z2. Okay. And so there's a non-trivial topological defect in the SO3 sigma model, which is such a Z2 vortex in 1 + 1 dimensions. It's an instanton. We know that this 1 + 1 dimensional sigma model is actually gapped. So eventually there will be no magnetic order. And however, these instantons will be present. They'll be fluctuating in space-time. And these actually lead to, this topological term means that they carry a certain phase factor that oscillates in space, and it leads to dimerization. So we understand from this that fluctuations convert this zero field spiral state into a dimerized state. But it's very, very, very weakly dimerized. If we turn on a non-zero field, we add basically a perturbation to the sigma model that likes the spins to spiral only within the xy plane, and they cant up. So then we've reduced basically SO3 to O2 cross Z2. Now the way you would describe this is a little different. The phase degree of freedom of the spiral becomes just a single phase of a cone. If you just plug this into the sigma model, you actually will find that the effective action just becomes that of a free scalar field describing fluctuations of the angle of the spins within the plane of the cone. And so this is a kind of typical behavior in a one-dimensional system. Sometimes this would be called a Luttinger liquid or a Luther-Emery liquid. We get a gapless one-dimensional state. But there's a nice twist, which is that we could choose the spins to spiral either clockwise or counterclockwise within the plane normal to the field. And those two are two distinct states. They're not related to one another continuously. So actually the one-dimensional system breaks the symmetry. It chooses to go clockwise or counterclockwise. And this is a discrete broken symmetry, kind of chirality ordering. So for that reason, actually, this state is called a vector chiral phase. So we can understand from the saddle point, indeed, the phase which is found numerically it has a kind of broken, sometimes called time reversal symmetry, although it's not really time reversal symmetry. So these are kind of the simple results of fluctuations that tell you what the phases are in the vicinity of this point. But the more interesting question is, what was already brought up a few minutes ago, which is, if we compare to the actual numerical phase diagram of this model, so it's totally consistent that we have metamagnetism down here, and in fact there's numerical indications for it. But this metamagnetism doesn't extend forever. There's an endpoint here. And in the saddle point calculation, what we found is something much simpler. So at best it describes just this region very near this critical point. So how do we extend this and actually describe this metamagnetic endpoint? And even better, try to understand the multipolar phases. What would be the natural description of this endpoint? So what does it mean that we have metamagnetism? So again, it means that as we lower the magnetic field, there's a jump in the ground state from the ferromagnetic state to one with a finite reduction of magnetization. So this is a kind of typical first-order transition. It means that in the vicinity of this metamagnetic line, there are actually two distinct solutions. There's one ground state which is ferromagnetic and another metastable ground state which is has a reduced magnetization, which is this vector chiral state. And above the saturation field, the ferromagnetic state is the true ground state, the other state is metastable. Below, the ferromagnetic state becomes metastable, and the true ground state is a vector chiral state. We have a crossing of two energy levels. So there's a regime here, I've drawn it in some particular way, which makes these phase boundaries look like straight lines. So I'm plotting field versus distance to the critical point squared, because the phase boundaries turn out to be quadratic. So there's the actual phase transition line, bless you, between the ferromagnetic and the vector chiral state. But there's a lower transition point, which is not a real transition, where the ferromagnetic state becomes locally unstable. So this is the point at which single magnon condensation would actually occur if we let it. If we just follow the metastable ferromagnetic solution down to lower fields. So this is kind of a region where you, if you want, you could supercool the ferromagnetic state. This is a result at the saddle point level. Okay. So in this region, the ferromagnetic state has higher energy than the cone state, but it still exists. But this is kind of a saddle point calculation. What happens if we go beyond saddle point and include quantum fluctuations? So the ferromagnetic state actually is very simple. We know it's an exact state. There are no quantum fluctuations in the ferromagnetic state. However, there will be quantum fluctuations in the cone state. And so we expect that these quantum corrections will, they're kind of fluctuations that ride up the quadratic energy of harmonic oscillators. They'll increase the energy of the cone state. And so there'll be a correction that penalizes the cone state at the expense of the ferromagnetic state. Now, we know the saddle point calculation is asymptotically exact, so this correction will be small as we approach the critical point. It's basically small by this factor that was in front of the action, which was square root of k over delta. So we can kind of expect there'll be a correction to the energy, which will be this factor times the saddle point energies. And the saddle point energies are of order delta squared, which is kind of easy to work out. So we expect there'll be a correction of order delta to 5 halves. And indeed, that's the case. You can do this calculation. Maybe I won't tell you how it works, but it's kind of a standard way to do fluctuations around a saddle point. It's like doing Vogel-Lyubov theory. And if you do it, you find a correction. So there's an additional term which is proportional to delta to the 5 halves in the energy difference between the ferromagnetic and the cone state. So in this, this becomes small as we approach delta equals 0, the critical point. So that's just a statement that the saddle point becomes exact here in terms of energy density. But then it will grow because this is a larger power than 2. And it will eventually lead to the actual energy of the ferromagnetic state meeting that of the cone state at the continuous boundary. So what happens here in this simple picture where we're only considering the ferromagnetic and cone states is that the actual boundary, when we consider correction to the saddle point, bends down, and we have a region here of metamagnetic transition, and then it hits the second order transition line, and above this line we have ordinary Bose condensation of magnons. And now you might worry, what sets this energy? What sets this parameter delta? And in general, you should worry because if this parameter delta is large, then the whole theory, which is built on proximity to the critical point, is not valid. So it turns out that to actually make this a controlled calculation and make delta small, we need to take advantage of this dimensionless parameter v, which remember was just a parameter of the theory. And there was a special value -1/4 which separated the region where you had metamagnetism for where you don't. So if we're very close to this point, we put it equal to -1/4 minus epsilon, then this crossing point happens at order delta of order epsilon squared. And so then everything is controlled and we can handle it. So at this point, we actually have developed a theory that shows that in the vicinity of this zero field Lifshitz point, there's, in general, we have a metamagnetism which terminates at some metamagnetic endpoint. But so far, the theory does not describe any of these multipolar phases. It's just describing an endpoint to an ordinary single magnon BC, the spectrochiral state. So what about the multipolar phases? Okay. Why are we missing them? Well, the reason is we didn't consider that possibility. Okay. What we've actually compared is the free energy, or at zero temperature, so energy density of two macroscopically distinct states, the cone or vector chiral state and the ferromagnet. And so there's one line here which is the first order instability line between these two phases. And we've also considered the continuous instability to single magnon condensation. What we didn't allow for, of course, are the bound states, which are essential to getting a multipolar state. So we should ask, where are the instability lines in this diagram to 2 magnon condensation or 3 magnon condensation? A simple way to kind of start thinking about this is to think about the physics of low density of magnons. When we talk about single, 1, 2, we're talking about 1 or 2 magnons in an infinite system. So this we can do by kind of focusing on the region where the transverse magnetization is very small. We think about a small canting angle away from the z-axis. We can expand that in its magnitude, which we call psi. And just plug this into the action and do a Taylor expansion. You can actually get an explicit description in terms of bosons. And it looks kind of like it should. There's a single boson energy here, which is positive when h is large and negative when h is small. So that describes a single magnon instability line. There's a certain mass. Its inverse mass is related to delta. And then we get some interactions. So it turns out that there are 2 kinds of bosons, and this is basically reflecting the fact that the boson condensate is a non-uniform one. It's a spiral, which could spiral clockwise or counterclockwise. So these are the 2 channels for this instability. And so there are 2 types of interactions. There's an interaction between identical types of bosons and an interaction between two different types of bosons. And we find exactly this interaction between the same type of boson actually changes from repulsive to attractive at this magic value of -1/4. So we can see that in terms of single magnon excitations, exactly this transition from continuous BEC of magnons to metamagnetism corresponds to the change of sign of interaction from repulsive to attractive. So this is, if we just put in all bosons of the same species, this is just a problem of bosons in 1 dimension with a usual quadratic dispersion and a delta function interaction that's attractive. This is one of the few nice problems that are exactly solvable. You can find most of the solution even in Landau-Lifshitz. It's got a basic baby version of the beta ansatz. What happens is that, of course, these bosons form bound states. And what's interesting, actually, is that the more bosons you put in, the more they're bound. They're attractive, so bosons can all go in the same place. So if you put 3 bosons together, they actually bind more strongly than 2 bosons together. They form kind of little collapsed bound states, where the size of the bound state actually decreases as you put more and more bosons together. So this is kind of the signature at the finite number of bosons level of metamagnetism. It's kind of collapse physics. How do we connect this bound state formation to metamagnetism? So now we're finally back to the bubble teeth. Okay, so thanks. Yeah, I think I'll make it. So the metamagnetism is a kind of textbook example of a first order transition. the most fundamental feature of the first order transition is, as I already talked about, coexistence of two different states. So if we sit right at the metamagnetic line, the energy density of the ferromagnetic state and the vector chiral state is the same. So the system can sustain a bubble of one phase in another. That's a general behavior at a first order transition, is two-phase coexistence. And this bubble has no energy cost for the inside of the bubble. It only has a surface tension. So if we think about a bubble of this magnetized phase inside the kind of fluid of the ferromagnetic phase, that bubble is exactly a finite region with a reduced magnetization. It's a, yeah.
But I think in the beginning you're saying that the magnetization is uniform, right? So the bubble is not localized in these regions.
Yeah. So now this is indeed. So if this picture is a classical picture of such a bubble.
How do we understand the pairing of bound state between bubbles or between the magnons? Is it like some kind of pairing in space?
So the bubble formation is already, a bubble is already a paired state.
Okay,
in fact,
okay.
it's a large number. So a semi-classical bubble is a bound state of many magnons. But the thing is, actually, it has some mobility. You will have some kinetic energy and can move around. So the uniform state.
What's the meaning of the bubble size?
So the bubble size is directly proportional to the number of magnons in the bound state.
So it's related to the correlation function or something? Because you say the magnetization is uniform, right? So how do we define it?
So there are different multipolar phases depending on the number of magnons in the bound state which condenses. Okay. Each one is a different order parameter.
Okay, but so are you saying that your bubble is really you have finite size in real space to see such kind of bound state?
Yeah. The bound state has a finite size.
So that looks like a phase separation. So usually in 1D, that means that you have ferromagnet one side and bubble.
Okay, so if we really have metamagnetism, what happens is these bound states exist only at the critical point. Okay, the bound states themselves attract. So as we go below the point, then you get a collapse, and you get to the infinite bound state. Okay. So what has to happen is quantum fluctuations have to actually select some preferred bound state size, which selects the multipolar order. So here's kind of a sketch of how we think it happens. If we were to take just the naive delta function interacting model, which is kind of just the naive expansion of the action, what will happen is because with delta function attractions, the two particle state is lower energy than the one particle state, the instability line will be a little bit higher. And each instability line for 3 magnon, 4 magnon, etc. will be higher in field than the previous one. But this obviously can't last forever because if we try to really pile more and more magnons together, the size of the bound state gets very small. Eventually it reaches the lattice spacing. We know this continuum approximation is no good. Very, very, very deep, highly bound magnons, we have to have some changes to this curve. And so one can do some kind of scaling analysis, I guess based on time. I won't tell you how this works, but roughly speaking, the idea is to compare the size of the magnon bound state to the characteristic scale of ordering the wave vector, if you want, of the incipient spiral state. And so what has to happen is that when we get very many bound magnons, the energy of such a state just approaches that of the uniform cone state. So we expect that these lines actually have to bend down like this. And now, as we approach from high field, it will really depend on the value of delta, which is the dominant first instability. If we're at high delta, we'll hit the 2 magnon bound state first. At smaller delta, we'll hit 3. At smaller delta, we'll hit 4, etc. So can we actually check this? It relies on some kind of scaling arguments for this field theory. Well, so far what we've actually been able to check is to calculate within the field theory the 2 magnon instability. And what we find is exactly this, that we can estimate, again in this, from the saddle point fluctuation calculation, the point that would be the nominal metamagnetic endpoint where the metamagnetism intersects the 1-magnon instability, and we find that the 2-magnon instability happens at a larger delta, further from the critical point. So just considering only 2-magnon states, so spin-nematic states and uniform states will have a spin-nematic region here, and then a metamagnetic region here. And we can expect that there'll be more in general, and so this is kind of the picture that we would have for this system based on all the analysis we put together. There'll be a sequence of multipolar phases terminating at a metamagnetic endpoint, ending something like this. So this is kind of the first endpoint of the talk. I thought maybe I have a couple of minutes just to be a little bit more speculative and talk a little more broadly about spin-nematics and other things. So maybe briefly I'll mention a couple of things about experiments, where this may be going. First of all, there are many experiments on lithium copper vanadate and other of these one-dimensional frustrated ferromagnetic chains. But really what interests me more is to try and understand how this extends to higher dimensions. I think given the time, I'm not sure exactly what I should talk about here. Let me mention what really happens in lithium copper vanadate. So this is really a nice example of a J1, J2 chain. If it were an isolated one-dimensional chain, it would have a spin-nematic ground state. But it's a one-dimensional system, so it's not long-range ordered in any real sense. So what do we mean by it being spin-nematic? Well, the really fundamental property of this state is that it has bounding of magnons. So below the saturation field, there is still a gap for spin 1 excitations, although there's no gap for spin 2 excitations. That's the fundamental property. But if we look at order parameters, it's more complicated. You should think about it as kind of a gas of molecules of magnons. And so that, in one dimension, such a gas is kind of a supersolid of these bosons. It has both kind of bosonic correlations, like those of a superfluid, and density-density correlations, like those of a solid. And these two things compete. It turns out when you consider coupling between these one-dimensional chains, actually the